Whoa, 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 whoa. Ooh, I quit drinking soda. So now I drink these. Hint of a flavor. Well, that's it. Let's go ahead and get right into this problem. So 2300. Successful pairs of spells and potions. Okay, let's go ahead and get right into it. So you're given two possible integer array spells and potions of length n and m respectively. Okay, where spells I represents the strength of the ith spell and potions j represents the strength of the jth potion. Okay, so there's the spell here has strength 5, the spell here has strength 1, the spell here has strength 3. These potions, this potion here has strength 1, strength 2, strength 3, strength 4, strength 5, etc. You are also given an integer success. A spell and potion pair is considered successful if the product of their strength is at least success. Okay, so for each spell, right, in order for it to be successful, the spell times the potion has to be greater than or equal to success. Okay, so that's kind of the function here in order to determine whether something is a successful, potion spell pair. Return an integer array pairs of length n where pairs of I is the number of potions that will form a successful pair with the ith spell. Okay, so what we're going to do is we're going to look at this example first. So in this example, we have spells equaling 513. Okay. And we have potions equaling 1, 2, 3, 4, 5. All right. 1, 2, 3, 4, 5. And we have success equaling to 7. All right. So the manual way of doing this, right, the clearest way would be to look at a spell. Now we're going to return this res array, and it's going to be the same size as the spell array because it matters for each spell, right? So for this spell, in order to be successful, when you multiply it, right, by its potion, it's got to be greater than or equal to success, which is 7. So 5 times the potion has to be greater than 7, greater than or equal to 7. So 5 times 1, is that greater than 7? No. 5 times 2, is that greater than 7? Yeah, 5 times 2 is 10. That's greater than 7. So this one's good. This one is not. 5 times 3 is 15, greater than 7, good. 5 times 4, 20, greater than 7, good. 5 times 5, 25, greater than 7, good. So what's the answer there? That would be 4. And that's why the answer here is 4. Okay, but what about 1? 1 times potion has to be greater than or equal to success, which is 7. So 1 times 1 greater than 7, no. 1 times 2 greater than or equal to 7, no. 1 times 3, 1 times 4, 1 times 5, no. So all those are big fat zeros, so no. And then what about 3? Okay, 3 is a little interesting. 3 times 1 greater than 7, no. 3 times 2 greater than 7, no. 3 times 3 greater than 7, yes it is, because it's 9. So that's at least 1. So we'll put that here. And in a moment, it'll be clear why I didn't even have to do the rest, but 3 times 3 greater than 7, 3 times 4 greater than 7, 3 times 5 greater, yeah. 3 times 4 is 12 greater than 7, yes. 3 times 5 greater than 7, 15, yes. Okay, so that means that there's 3 in this case. Okay, so there is a pretty simple solution here, which would be big O of n times m, right? Where n is the length of spells, n equals length of spells, and m equals the length of potions. Right, because all we have to do is just look at each spell, then look at each potion and see if it works, and then add that in, right? So we look at this potion, the spell, we look at each potion, we figure out what that number is, we put it here. We look at this spell, we look at each potion, we figure out what that number is, we put it here. We look at this spell, look at each potion. So for each spell, we look at all potions. So we look at n spells, and for each n spells, we have to look at all m potions. So that means we look at nm total things. All right. Now, will that work? Well, n and m are both less than or equal to 10 to the 5. So that means that, I should probably make a video about this, right? But that would mean that this would be less than or equal to 10 to the 5 times 10 to the 5, which is equals 10 to the 10. And most times your solutions have to be somewhere, approximately 10 to the 6th or better. So 10 to the 10 is much bigger than 10 to the 6th, so this is not going to work. right? So this is too slow. Okay, so we need to think about a quicker way to solve this without actually looking at each individual spell and potion pair. Okay, now, since this is already sorted, what's something interesting that happens here? Okay, in this particular situation, it is such that the potions are already sorted. Okay, and the thing that's interesting about it is when you look at 5, right? When I look at 5 and I say, okay, does 5 work with 1? No, it doesn't. Does 5 work with 2? Yes, it does, because 5 times 2 is 10, which is greater than 7. All right? Now, do I need to continue looking through the system? Meaning, do I need to look at 5 and 3 and 5 and 4 and 5 and 5 in order for this to work? Well, the answer is no, because it's already sorted, right? If my spell works with a potion of size 2 and it's already sorted, so that means all the potions to the right? All the remaining potions are greater than 2, greater than or equal to 2. Well, if it works with 2, it'll definitely work with them. So I don't need to compare myself to them. I can just assume, well, since this system is sorted and I work with this potion, well, all the other potions are only larger, so I'll definitely work with them too. So I only need to look at this 2 and say, well, I can infer that there's 4 here that work. Right, with 1, it's a little bit of a different situation because I need to go through the whole system and I'd find nothing. When I look at 3, right, I'd say, okay, does 3 work with 1? No. Does 3 work with 2? No. Does 3 work with 3? Yes. Well, if 3 works with 3 and it's already sorted, then it's going to work with everything to the right. So that's how I can infer that there are 3 solutions in this case. Okay. Now you might say that's still linear searching through for each potion, right? For each spell, you have to linearly search. But since it's actually already sorted, you could do a binary search. Okay, and what I mean by that is, well, you know, when I look at 5 and I look at 3, what I can do instead, right, the alternative is I'll say the following. So I'll have 5, 1, 3 again, so I'll write this problem out again. I'll have the sorted version of spells. And what I'll say is, okay, if my spell, let's look at our equation again. So we have spell times potion needs to be greater than or equal to success. Right? So all I need to do is find the minimum potion that will work, and I'll know that everything else will work to the right. Right? What ends up working here is, what's the minimum potion that would work with a spell 5 to get greater than success? Well, if I get 2, all I need to do is locate the 2, and then I know everything else to the right will work as well, right? I can infer then that all of these will work as well. Right? When I look for a 1, what would be the minimum spell I need to find? What would be the minimum potion I need to find in order to get me greater than success? It would have to be at least 7, right? So I need to look for a 7, and everything to the right will give me the answer. There is no 7. There's nothing to the right, so that's why the answer is here is 3. How about for 3? For 3, the minimum spell I would need to make this work, well, 3 times 1 is 3. 3 times 2 is 6. I need to be greater than 7, so 3 times 3 is 9. So the minimum potion I would need for this spell to work is 3. So I'm going to look for 3, and the second I find the 3, I'll know everything to the right works. Okay, so putting that in this equation here, right? If I have 5, and I'm trying to find a potion that will work to get me greater than or equal to 7, well, I'm going to solve for a potion, right? So I need to find a potion that's greater than or equal to 7/5, right? I need to find a potion that's greater than or equal to 7/5. And if I find that potion, then everything to the right of that will be good. Does that make sense? Right? So when I'm looking at this, I'm saying, okay, I have this spell 5, and I need my success to be greater than 7. So in order for my success to be greater than 7, I need to find a potion of what size? Well, just solving this equation, I need a potion that's greater than 7/5. So I look at this array and I say, where is 7/5? Now, I could, of course, linearly go through and say, okay, where would 7/5 go in this system? Oh, it would go right here, right? It would go right here. So that means that everything to the right of this is greater than 7/5. Now, I could do that linearly, right? I could walk through linearly and try to find where would 7/5 go, right? Where is the potion placement here? Because I know if I can get 7/5 at this point, that means everything to the right is greater than or equal to 7/5. So all of that will work. So I just need to look at this one spot, and everything to the right will give me the answer. I could do that linearly, but I could also do that via binary search, right? So what I'll do is I'll binary search instead for 7/5, and that will give me a search time of big O of log M, because M is the length of potions. So what I'll do is I'll binary search for 7/5. So I'll look here and I'll say, is this greater than or equal to or less than or whatever 7/5? Well, 7/5 is less than this, so that means that I can exclude everything to the right. Then I'll go here. Then I'll go here and I'll say, you know, is this less than or equal to 7/5? 2 is greater than 7/5, so I can exclude everything to the right. And I probably go here and I say, is this less than or equal to 7/5? Oh, it's less than, so that means that my new left pointer's on the right, right? You know, you should know how binary search works if you're going to do this problem, right? It's a medium problem. You should have a pretty strong understanding of those fundamental concepts, right? But the idea of binary search is you can cut the systems in half because the system is already sorted, right? When I look at this 7/5 initially here in the middle, I could say, well, 7/5 is less than 3. And since the system is sorted, then everything to the right is greater than 3. So then it's also greater than 7/5. So that's not where I'm going to find 7/5. So then I keep cutting the system in half until I find a point, which gives you log M time if you have M is the length of potions, right? So all I really need to do to make this work, in summary, is I'm going to take potions. My first step is I'm going to take potions and I'm going to sort it. My next step, now you can do this in real time, is I'm going to figure out the minimum potion I need for each spell. For each spell I. Right? So the minimum potion I need for each spell I is, well, that's just this equation we found here, right? So that would be the potion, the minimum potion. Did I just spell potion wrong? Yep, I did. Apologize. The minimum potion is the success amount divided by the spell. It's called spells of I. And then I'm going to binary search for the location of that potion. And I'll call that location X. So that means that in that location, right? So if this is the location where 7/5 would go, that means that everything to the right works, right? So if the location of 7/5 is 1, then that would mean that everything to the right works. So the length of this thing is 5, so that's 5 minus that position X. So if I binary search for the location, right, that means that's the location of where it would go. That means that everything to the right is larger than it, so that means that everything to the right would work. So how many elements are there to the right? Well, that would be the length of potions minus this X position. So that's how many potions would work. And my writing is horrendous. Okay, now how can I get this all? No one's going to want to watch this video with such terrible, terrible writing. So excuse me for a moment while I try to move things around and make something look a little bit nicer here. You guys get what's going on here. That's going to be my, it's going to be the thumbnail right there. Does that look all right? Not really? Okay. All right, so let's go ahead and try to write the code for this, okay? So first thing I'm going to do, like I said, is sort potions. So we know that the potions are in order, right? Because I want to do a binary search on them. And then I'm going to look at each spell in spells. And I'm going to find out the minimum potion that I need, right? So the minimum potion I need, potion. For some reason that word looks so misspelled to me. I don't know why. The minimum potion I need is what again? Well, it's success divided by the current spell. Now make sure all the spells are greater than 0. Okay, good, because you want to divide by 0. And then I'm going to find out where that potion would be within our system. So x equals, now we're going to use bisect left. So this is a library that allows you to do binary search. And for kind of more advanced binary search problems like this, I recommend you just memorize the code for this. It's like a simple binary search problem, like solution, but it has a little bit of a tweak that allows you to find the location of something without having to play the game of like it not existing, right? Because we're not trying to find if the potion we are looking for exists. We just want to find where it would be, because that way we would know everything to the right would be contained within the solution, right? I don't need there to be the 7/5 potion. I just need to know where it would be, because that way I would know everything to the right would work, right? So x equals bisect left. What are we going to bisect? Well, we're trying to find the location within potions. And what location are we trying to find? The location of this minimum potion. Okay? And that means we just add to our solution res. And res will just be an accumulation of... Oh, no. It's going to be an array. So we'll append to res. And then we'll return res at the end. So this will just be what we're accounting for. It would be the length of num... Not the length of... The length of potions. So it would be all the potions minus x, right? Because x is the position where it would go, so everything to the right would work. So then what is the length of everything to the right? Well, that's length of potions minus x. All right. I'm kind of curious if bisect left expects an integer. Looks good. And I'll show you guys the bisect code in a moment. It's not really important. You can look it up and just memorize it, right? You should understand the idea, but like there's a lot of data structures, right? And I recommend that you just kind of memorize the code for them, especially if you're going to be using them in this fashion, right? Because I'm going to be using bisect left when I'm trying to find the location of something in a sorted array. I don't really need to know exactly how it's implemented. Like intuitively, I just need to know what the code is so I can implement it and then use it, right? Because I'm going to use it, I'm going to abuse it, but I'm not going to like... I don't know, but I hope you understand what I'm trying to say here. So let's think about the runtime here, okay? So it's kind of interesting because we have spells and potions that are both variable length, right? Versus this constant success. We're going to ignore that because it's just a variable with one value. So let's say n is the length of spells, and I'm just following the convention given in the problem, right? The problem description stated that, we have length n and length m, so n is spells, m is potions. All right, and let's say m is the length of potions. Well, what do we have to do in this problem? Well, here we sort potions, right? So we have at least m log m here. We look at all n spells, right? We look at all n spells here. And then for each spell, we bisect potions, which basically means that we do a binary search on potions, which is going to take log of m time. So we do m log m things to sort potions, because it's not particularly sorted. It just happens to be sorted in this first example, right? But here, for example, it's not sorted. And for each n spell, we look at each individual spell. We append something constant, but we have to bisect. So we do m log m things plus n log m things, okay? So for time, that's big O of n log m. We'll do the m log m. M log m first for this. Plus n log m. So for each n spells, you do a log m operation. And that could be simplified, I guess, if you wanted to m plus n log m. Kind of an interesting runtime. It's kind of funny. All right, and then what about for space? Well, it's one of those problems where extra space could be an argument, but, you sort potions. That could be done in constant space if you did like a heap sort, in-place heap sort, with still m log m runtime. But let's just say, for the sake of argument, that it doesn't really matter because we have to create this res array, and then we have to populate it with all the return values, right? So for n spells, we have to return n values. So this is going to be the size of n by the end no matter what. So that's big O of n space. And let's say big O of n space, because you could add an extra m to sort this, but if we call this in-place heap sort, this m factor goes away with in-place sort. So we just need n space to create this res to return it. right, to return the value for each, I guess, like query for each spell, right? All right. So if you guys do want to see the bisect code, I pushed it in one of my submissions. If you're curious, I mean, the video is kind of over now, but right here. So here's the bisect left code. I literally just copied this from the internet. This is the actual code from the source bisect left, right? So basically what it does, okay, these two are we're going to ignore. These are just like special cases if the information wasn't given correctly. Oh, I didn't even know that. You could bisect left and give boundaries. You could provide boundaries. But, you know, low is 0, high at the top. So just like normal binary search, right? You have low at the bottom, high at the top. And then while low is less than high, it should be standard binary search. You look at the midpoint, right, halfway in between. You make a, you ask a question, all right, if this is less than this, well then now low is mid, right? If the number I'm looking for is greater than what's at the mid, well then since the system's already sorted, everything less, right, isn't going to work. So now low equals mid plus 1, right? If you're looking at the middle and you're larger than the thing at the middle, if it's already sorted, then you're larger than everything to the left. So that means my new low is mid plus 1. Otherwise, my new high is mid, so I could be less than or equal to on the other side. So this is just a standard binary search, but the difference is you return low because you're not necessarily going to find the element you're looking for. All right, guys, that's it for today's video. I hope you have a beautiful day.